What if I told you that right now, in this very moment, somewhere out there among the 100 billion galaxies visible to our telescopes, a civilization might already be drinking starlight the way you sip your morning coffee? Not one star, not a handful, all of them. Every sun in a galaxy of 400 billion stars, harnessed, tamed, and turned into pure usable power. It sounds like the stuff of science fiction, and for now, it is. But the question is not as absurd as it first appears, because somewhere on the long, uncertain road between where humanity stands today and where physics says a civilization could eventually go, there exists a hypothetical endpoint so vast it barely fits inside human imagination. It's called a Type 3 civilization. And today we're going to walk that road, step by impossible step, and ask what it would actually mean and take for Earth to get there. To understand where this idea comes from, we have to go back to 1964, to a Soviet astrophysicist named Nikolai Kardashev. Kardashev was thinking about a very practical problem. If intelligent life exists elsewhere in the universe, how would we ever recognize it? Alien civilizations wouldn't send us a business card. They wouldn't paint their spaceships in colors visible from light years away. But there was one thing Kardashev realized any advanced society would need more and more of, no matter what it looked like, no matter what it believed, no matter what it valued: energy. Kardashev's insight was that civilizations could be categorized based on the level of energy they can harness. A Type 1 civilization uses energy on a planet-wide scale. A Type 2 uses the entire energy output of its star. And a Type 3 uses the energy resources of its galaxy. It's an elegant, almost brutally simple idea. Forget culture, forget technology in the abstract sense, forget politics or art or language. Just measure the power bill. That number alone tells you almost everything about what a civilization is capable of. So where does that leave us right now in 2026? Reading this by whatever light source got you here? Not very far along at all. Different research groups calculate it slightly differently, but the consensus places humanity at around 0.7 on the Kardashev scale, meaning we're still short of even fully harnessing the energy resources of our own planet. The Kardashev Scale is a method for ranking a civilization's level of technological advancement by how much energy it can harness, from a single planet's worth for Type 1 to an entire galaxy's for Type 3. Some more detailed models put Earth at roughly 0.73 in the early 2020s, projecting a slow climb toward 0.74 or so by the middle of the century, and warn that without some genuine leap in energy technology, it could take many centuries, maybe millennia, just to reach full Type 1 status. That's worth sitting with for a moment. We haven't even become masters of our own planet's energy yet. And Type 3 lies not one step beyond Type 1, but two entire orders of civilizational magnitude beyond it. To put the scale of that jump into perspective, the difference between a Type 2 civilization, one that captures the full output of its star, and a Type 3 civilization, one that commands the power of its entire galaxy, is itself a leap of roughly 10 billion times. Not 10 times, not 100 times, 10 billion. It's the kind of number that stops meaning anything to our intuition. So let's try to rebuild that intuition piece by piece. Start with what we already do right now as a Type 0.7 species. Every year, humanity consumes something on the order of 600 exajoules of energy, drawn mostly from fossil fuels, with a growing slice coming from solar, wind, nuclear, and hydro. That number sounds enormous until you compare it to what the sun does every single second, without even trying. The sun radiates about 3.8 times 10 to the power of 26 watts in all directions, constantly, and Earth intercepts only the tiniest sliver of that, roughly 1/2 billionth of the total. And yet even that sliver is more energy hitting our planet in a single hour than all of humanity uses in an entire year. A true Type 1 civilization would need to capture and use the entire energy budget available on Earth, something in the range of 10 to the 16 or 10 to the 17 watts continuously, which sounds achievable until you realize we currently manage something closer to 10 to the 13 watts. We are quite literally off by a factor of 1,000 or more from mastering our own front yard. Now imagine leapfrogging past that entirely and capturing not Earth's energy, but the sun's. A Type 2 civilization would need a structure or a network of structures capable of intercepting a meaningful fraction of the sun's total output. This is where a famous idea enters the story, one you've probably heard of, even if you didn't know its origin: the Dyson sphere. In 1960, physicist Freeman Dyson proposed that any sufficiently advanced civilization, driven by an ever-growing need for energy, would eventually build a shell, or more realistically, a vast swarm of orbiting collectors around its home star. Not a solid ball, despite how popular culture often imagines it, since a rigid sphere around A star is structurally implausible, but a cloud of satellites, solar collectors, and habitats encircling the star from every angle, harvesting its light before it ever escapes into the dark. Dyson's real insight wasn't architectural, it was thermodynamic. Energy doesn't just disappear after it's used. It gets converted, work is extracted from it, and eventually it's radiated back out as waste heat at a lower temperature than it arrived. That means a star wrapped in the infrastructure of an advanced civilization should glow strangely in infrared light, even while looking dimmer than expected in visible light, because its energy would be getting captured, used, and re-emitted as heat, rather than escaping as the star's natural warm glow. This single idea turned how do we find aliens from pure speculation into an actual observational strategy, one that real astronomers have quietly been pursuing for over a decade. And in just the last couple of years, this search has produced its most tantalizing results yet. In 2024, a research effort called Project Hephaestus combed through data from roughly 5 million stars, cross-referencing observations from the Gaia satellite, the 2-micron all-sky survey, and the Wide-Field Infrared Survey Explorer, hunting for exactly the kind of infrared excess Dyson predicted. Out of that massive sample, the team's pipeline used filters and even a neural network to sift out interlopers, ultimately narrowing the field down to 7. Candidates deserving of serious follow-up, all of which were small, cool M-dwarf stars showing infrared signatures that ordinary astrophysics struggled to fully explain. For a brief moment, headlines around the world speculated that astronomers might have stumbled onto genuine evidence of alien megastructures. But real science moves carefully, and the story since then has been a lesson in exactly that kind of patience. Researchers began cross-checking these candidate stars against radio survey data, since a background galaxy or an active black hole sitting almost exactly behind one of these stars, purely by chance, could mimic the same infrared glow. High-resolution radio observations found that one of the candidates showed a source consistent with synchrotron emission from a radio-loud active galactic nucleus with extended jets sitting offset from the star itself, strongly suggesting the infrared signal actually belonged to a background galaxy caught in the same patch of sky, rather than to the star. Then, just weeks ago in the timeline of this story, the James Webb Space Telescope turned its extraordinarily sensitive infrared eyes toward 2 more of these candidates. JWST observed these 2 Dyson Sphere candidates in the summer of 2025, specifically to test whether their unusual infrared glow held up under much closer scrutiny. The investigation is ongoing, but so far, as with the earlier candidate, natural explanations, whether background contamination or unusual but ordinary stellar disks, remain far more likely than alien engineering. So, no, we have not found a Type 2 civilization hiding in the data. But notice what this episode actually tells us. We now possess the observational tools to actually go looking, seriously, systematically, with real telescopes and real statistics, for the fingerprints of a civilization far beyond our own. That in itself marks an extraordinary moment in human history, whether or not the search ever succeeds. So, let's play the long game and actually imagine it. Suppose humanity, against every obstacle, does keep climbing. What would it genuinely take for Earth, or rather, for whatever descendant of humanity still calls itself human by then, to become a true Type 3 civilization? The first stage would be finishing what we've barely started, total mastery of our own planet's energy. That likely means transitioning entirely away from burning ancient carbon and toward a combination of advanced solar collection, next-generation nuclear fission, and possibly practical nuclear fusion, a technology we've chased for 70 years and are only now beginning to approach with experimental reactors, achieving net energy gain under laboratory conditions. Achieving Type 1 status wouldn't just mean generating more power, it would mean coordinating that power globally, which is arguably the harder problem. Kardashev's scale was never purely about physics. A civilization capable of capturing all of a planet's energy would almost certainly need to be a civilization that has stopped treating energy, and by extension resources and geography, as something to fight wars over. That alone might be the single hardest technological milestone of all, because it isn't technological at all. It's social. Assuming we cleared that bar, the next stage would demand leaving the surface of Earth behind almost entirely as the primary site of civilization. To become a Type 2 civilization, harvesting the sun's full output, you don't build your energy collectors standing on a planet's crust competing with agriculture and cities. You build them in space. This is where the Dyson swarm stops being a hypothetical alien signature and becomes an actual construction project. Rather than one impossible solid shell, realistic models describe a Dyson swarm as billions of individual solar collectors, each a satellite in its own independent orbit around the sun, gradually assembled over generations, perhaps starting by disassembling asteroids and small moons for raw material, rather than hauling everything up from Earth's deep gravity well. Mercury alone contains enough mass that, broken down and spread thin enough, Its material could construct a solar collector shell around the sun. A civilization at this stage would be drawing on power. Measured in the range of 10 to the 26th watts, roughly the sun's entire luminous output. Enough energy that concepts we currently treat as fantastical, like terraforming entire planets, building rotating space habitats by the thousands, or running simulations of staggering complexity, would become almost mundane infrastructure projects. And then comes the truly staggering leap, the one from Type 2 to Type 3, because capturing the energy of one star, as unimaginable as that already is, still leaves you a rounding error away from a Type 3 civilization's power budget. A Type 3 civilization would need to harness energy on the order of 4 times 10 to the 44th ergs per second, working out to roughly 10 to the 36 or 10 to the 37 watts, the combined output of an entire galaxy's stars. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. To become Type 3 doesn't just mean building one Dyson swarm. It means building Dyson swarms, or their equivalent, around a meaningful fraction of every star system in the galaxy, all coordinated, all connected, all contributing to a shared civilizational energy grid stretching across 100,000 light years. Pause on that distance for a second, because it's the part that breaks the idea open for most people, the first time they really think about it. Our nearest stellar neighbor, Proxima Centauri, sits about 4.25 light years away. Our fastest human-made spacecraft, the kind that took advantage of gravitational slingshots to reach speeds no crewed vehicle has ever matched, would still need tens of thousands of years just to reach that single nearest star. Now multiply that problem by the roughly 250 billion other stars scattered across our galaxy, each separated from its neighbors by similarly punishing gulfs of empty space, and you begin to see the real bottleneck standing between here and Type 3. It isn't primarily an energy problem. It's a distance problem. A civilization doesn't become Type 3 just by building better solar panels. It becomes Type 3 by solving, in some form, the challenge of interstellar travel and communication across 100,000 light years, whether through generation ships that carry entire self-sustaining populations across centuries, through some form of suspended animation, through self-replicating robotic probes that spread out star by star, building infrastructure long before any living being arrives, or through physics we currently only sketch on chalkboards, like traversable wormholes or exotic propulsion that might someday bend the rules we currently think of as absolute limits. This is also where the story connects to one of the most haunting open questions in all of science, the Fermi paradox. If the universe is unimaginably old and unimaginably vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars, then surely, statistically, some civilizations should have had a head start of millions or even billions of years over us. Given enough time, even a civilization expanding slowly, colonizing just a few new star systems per century, should be able to spread across an entire galaxy in a cosmic eye blink compared to the galaxy's actual 13 billion year age. So the paradox asks the obvious, unsettling question: if this is even remotely possible, where is everybody? Why does our sky look empty, our radio telescopes silent, our infrared surveys of nearby stars showing nothing but natural starlight rather than the waste heat of alien engineering? Recent rigorous searches like Project Hephaestos are part of humanity's ongoing attempt to actually test this question empirically rather than just debate it philosophically. And so far, despite sustained observational programs stretching back to whole sky infrared surveys and continuing through the most recent candidate searches, no confirmed technosignature of a Type 2 or Type 3 civilization has ever been found. That silence is itself data, and it's led some researchers to propose a sobering hypothesis sometimes, called the Great Filter. The idea that somewhere along the path from simple chemistry to a galaxy-spanning civilization, there exists some barrier so difficult to cross that almost nothing ever makes it through. Maybe that filter lies behind us, in the sheer improbability of life or intelligence emerging at all, which would make humanity remarkably, wonderfully rare. Or maybe, more unsettlingly, the filter lies ahead of us still in some challenge, technological, environmental, or self-inflicted, that tends to end civilizations before they ever reach the stars in earnest. It's worth stepping back here to acknowledge something important, something that keeps this whole conversation honest. Everything we've just described, Dyson swarms, galaxy-spanning power grids, Type 3 mastery, exists entirely in the realm of extrapolation and educated speculation. The Kardashev Scale itself has been criticized by physicists and futurists alike as too rigid, too focused on brute energy consumption, as though civilizations must always keep growing exponentially forever, when in reality efficiency, miniaturization, and entirely new forms of technology might let a civilization accomplish more while consuming far less energy than these simple models assume. Some researchers have even suggested that instead of exponential energy growth continuing forever, real civilizations might plateau, finding cleverer and more efficient ways to do more with less. The way humanity's own energy used per unit of economic output has already started to decline in some developed nations, even as prosperity increases. If that's true, then perhaps no civilization, anywhere, ever needs to become Type 3 in the way Kardashev originally imagined. Not because it's impossible, but because true advancement might not require it. And yet, even acknowledging every one of those caveats, imagining Earth's hypothetical journey to Type 3 does something valuable, something almost meditative. It forces us to confront scale in a way almost nothing else in daily life does. We spend our lives worrying about problems measured in hours, in paychecks, in single lifetimes. The Kardashev Scale asks us to imagine problems measured in stars, in galaxies, in spans of time longer than our species has even existed. It asks whether the atoms that make up your body, forged originally inside the heart of some long-dead star billions of years before Earth ever formed, might someday be part of a civilization vast enough to answer to the light of 100 billion suns rather than just one. It's not a promise. It's barely even a plan. It's a thought experiment stretched across the full width of what physics permits, a kind of civilizational North Star that may never actually be reached, but that reveals, just by being imagined, how far the human story could theoretically travel from its beginning on one small, ordinary blue planet. So return for a moment to that opening image, a civilization drinking starlight the way you sip your morning coffee, not from one star, but from 400 billion of them. We are not that civilization. We may never become that civilization. Right now, we are barely a flicker above zero on a scale that stretches toward numbers the human mind can barely visualize, a species still arguing over how to share the energy of a single, ordinary planet. And yet, here we are, capable of imagining the entire staircase from where we stand to the very edge of what physics allows, capable of building telescopes sensitive enough to search real stars for the fingerprints of civilizations that might already be climbing that staircase somewhere else in the dark. Maybe that's the real measure of a species, not the wattage it commands, but the fact that it can look up at 100 billion galaxies, know almost certainly it will never visit most of them, and ask the question anyway, what would it take? And whether the answer is millions of years or never, or something we can't yet imagine at all, the asking itself is already, in its own small way, a kind of beginning.